All right, and welcome to section 6.4, graphs of logarithmic functions. So what we're going to do today is we're going to look at some graphs of logarithm functions, see if we can identify their domain, and then we're going to try to, use our transformations of graph on logarithmic functions to help us both graph things and to identify functions from their graphs. All right, let's get started. So let's review just for a few minutes for exponential functions. So exponential functions defined as y equals b to the t. Let's remember the domain and the range for those. So b is any number greater than 0, not equal to 1. So what was the domain for exponential functions? The domain was minus infinity to infinity, all real numbers, right? We didn't divide by 0, and we didn't take the square root of a negative number. And the range is, well, the smallest we got was 0. Remember, we had the horizontal asymptote, and the largest value was infinity. So we had a horizontal asymptote at y equal to 0. The x-axis was a horizontal asymptote. So remember, the logarithmic function defined as y equals log base b of t is the inverse of the exponential function. So as inverse functions, the domains and ranges are swapped, right? Domains and ranges are swapped. So the domain of log base b of t is the range of exponential function, right? So now we're going to have to worry about one more thing when we worry about domains. So the domain of log base b of t is 0 to infinity. We can't take the log of 0 because we can't take any number to a power and get nothing, right? If we're just talking about the common logarithm, log base 10, you can't take 10 to a power and get nothing. There's always going to be a piece of something there. Also, you can't take 10 to a power and get a negative number. That's not going to happen. So there's a new rule that we have to worry about in domains. Are we taking the log of a number less than or equal to 0? So we got to start worrying about that now. Three things to worry about in domains. And the range is going to be the domain of the exponential. So the range of log is minus infinity to infinity. Since exponentials have horizontal asymptotes, this means, well, if we take a horizontal asymptote and we swap it, logs have vertical asymptotes. Logarithms have vertical asymptotes. And the basic one, just log base b of t, is going to happen at t equal to 0. Okay, t equal to 0. So the y axis is going to be the vertical asymptote for an unshifted log. All right, let's take a look at this. So here's a graph, and this is the graph of just log base 10, I think. No, it can't be because 10 over here is 1. I don't know what this is a graph. It's a graph of a logarithm. And let's go ahead and get the domain, range, and asymptote from our graph. Well, if we look at the domain, I have to zoom out a little. I made that graph really big, didn't I? Okay, we'll zoom out a little more. What is the domain of this function? Well, we can see if you're looking across the x-axis or t-axis, the input axis, there's no values here, and it starts getting a value at 0, and then it has values all the way forever. So the domain is 0 to infinity, right? Just looking at the graph and reiterating what we already know. What is the range? Well, we can see if we look up the y-axis, if we look up here, we're starting down at negative infinity. We have values, we have values, we have values. Keep going, and this increases really slowly over here, but it does in fact keep increasing forever. So it will eventually get to infinity. It just takes a long time to get there. So the range is minus infinity to infinity. And what is my vertical asymptote? Well, let me just erase where I drew all over this. But you can see that as x goes to 0 here, as we're getting close to 0, this guy's shooting down to negative infinity, but it's never going to cross the y-axis. So our vertical asymptote is x equal to 0, or t equal to 0, whatever you use as your input variable. All right, so that's what they look like on a graph, and that's how you can find the domain, range, and asymptote from a graph. All right, what about from a function? I can zoom back out a bit. What about finding the domain and the asymptote from a function? Well, why is this asymptote happening? Well, it's happening because we're trying to take 10 to a power and come up with nothing, all right? So it happens when what's in here equals 0. When that equals 0, when x plus 3 equals 0, that's when we'll have our vertical asymptote. That's going to cause the problem, right? We can't let that equal to 0, so as that equals 0 is where the vertical asymptote is going to be. So to find the vertical asymptote, well, I spelled that wrong, didn't I? Asymptote, I just quit writing. To find our vertical asymptote, you solve where the inside part equals 0 and you exclude it. So we're going to solve where the inside part of the logarithm, what's in the parentheses, x plus 3 equals 0, and that's going to give us our vertical asymptote, and we're going to exclude it from our domain. I'm going to do two things. Exclude from domain, we want only values bigger than that. Only greater than values. So x plus 3 equals 0 when x equal to negative 3. So that's going to be our vertical asymptote right there. X equals negative 3 is where the vertical asymptote is going to happen. And our domain is going to start at 3, negative 3, not including it, so parentheses, comma, infinity. Anything bigger than negative 3 is fine. We put in negative 2, we'll get log base 10 of 1. We all know that's going to be 0. All right, so that's one thing to look at. Let's think about for just a second what we know about shifting graphs. Well, we know when we add inside a function, so inside that x plus 3, that means we shifted this graph 3 to the left. And look, the vertical asymptote shifted from x equal to 0 to x equal to negative 3, just like we would expect. So the whole graph is just picked up and shift left 3 units. The vertical asymptote shifted, the domain shifted, the whole graph shifted. All right, well, I want you guys to try the next one. I would like you to find the domain and the vertical asymptote of this next function. So pause the video, look at it carefully, and see if you can figure out where the vertical asymptote exists and what the domain of the function is. All right, are you back from pausing the video? So we're going to do the same process. We're going to see where t minus 2 equals 0. All right, we don't want that guy, so that's when t equals 2. So my vertical asymptote is at t equal to 2. Okay, that's my vertical asymptote. And what is my domain? Well, you have to be a little careful here when we're subtracting things and doing things. But really what we can see is what's happening to this log function. Well, it's shifted to right? 2 to the right. And that makes sense with our vertical. Okay, that's not looking like the word right, is it? To right. And that makes sense with our vertical asymptote here shifted at t equal to 2. Up 1. Well, that's not going to make a difference for our domain, right? And so our domain is going to shift 2 to the right. So we're going to start at 2 and go to infinity. The only one you have to be careful with where it might be negative infinity to a value is if you've reflected across the y-axis. All right, one more to try. Why don't you guys give this one a try? Pause the video, give this one a try. All right, so did you solve 12 minus 3z equals 0? I hope so. It's going to tell us where our vertical asymptote is. So that's where add 3z to each side. You get 12 equals 3z, divide by 3, and you get 4 equals z. So there is our vertical asymptote, 4 equal to z. I'm just going to label it VA. And now what about our domain? Well, we know 4 isn't in the domain, but when we look inside here, we can see that we put a negative on our input, right? Our input is now negative 3z. So while that's going to do some stretching and compressing and whatnot, it's also going to shift it. You know, if we actually, maybe a good way to look at this, let's go ahead and factor this out. I think that might be a better way to look at this. Let's factor 3 out of this. So that would be 3 times 4 minus z. I don't know if this helps or not. So now we have we can see that it's a shift 4 to the right because it's a plus 4. Or maybe we should have factored out a negative 3. Well, anyway. Not sure that that was a good step or not. Is that helpful or not helpful? What if I did minus z plus 4? I think I'm going to back up. Skip that part. I think I'm making it too complicated right now. Back up. Okay. So we saw that our vertical asymptote was at z equal to 4. But if you look inside the argument of natural log, you can see that the z is actually negative. And we can actually just test a couple values to see what's going on. We know it's going to be either minus infinity up to 4, or it's going to be 4 to infinity, right? 4 is definitely going to be our cutoff, and it's going to be one of those two values. Since it's a negative on the input value, I know it's going to be the first one, but you can actually test. So let's just test a value in here. Let's test z equal to 0. Well, that would be the natural log of 12, right, minus 3 times 0, which is okay. That's an okay value. If we test a value in the other one, 4 to infinity, let's pick 10. is equal to 10, we would get the natural log of 12 minus 3 times 10 is 30. So that would be the natural log of minus 18. That's not okay. So if you're having a little, this is just to help support what you know about graph transformations. You should know that since there's a negative in there, it's going to be reflected across the y-axis. But if you're not 100% sure, you know what this is our cutoff point is where the vertical asymptote occurs. You can just test a value either way, which one produces okay values and which one doesn't. So that guy's not right. And our domain must be negative infinity to 4. All right, so that's the first video.